In Module 4, we're going to be taking everything that we've learned so far and putting all of it together. So as you work on your index card with your formulas in it for this particular module, you will likely want to make sure that you take the index cards that you've already used for Modules 1, 2, and 3 and combine all of those formulas together and put them on the same card, because you will need all of them in this particular module. The first example problem that the author gives you is just very simply a one-dimensional motion problem. He tells you that it is at a particular angle, but there's only motion in one direction. He gives you the velocity, and he tells you the direction, and he gives you the time, and he asks you what is the displacement. Well, there's nothing complicated about that very first problem, example 4.1, because the motion is all in one direction, and you can just very simply use the kinematics equations that we used back in Module 2 to calculate what his displacement was. However, when he gets to example 4.2, things change a little bit, because he says that the explorer is looking at directions on a map, and she travels in two different legs of the journey, really. The first leg of the journey, she's traveling at 0.92 meters per second at 113 degrees, and she's traveling for a total of 2.3 hours at that velocity in that direction. Then she turns and she travels at 0.56 meters per second, so a slower velocity, at 220 degrees for 1.2 hours. Now, the reason that we can't just take these two velocity vectors and add them together is because the two velocities do not affect each other. The problems that we did in Module 3, we were discussing problems where you had a plane that was going one direction and the wind was blowing it in a slightly different direction. And so that affected the velocity of the plane because of the velocity of the wind. If you have a boat in a current problem, the current is affecting the velocity of the boat. And so the boat isn't going in the direction that it's aiming because the current is pushing it a different direction. But in this particular problem, you've got two completely separate legs of the journey. The first leg of her journey does not affect the second leg of her journey. So therefore, it makes no sense to add these two vectors together because the velocities are not being affected by one another. In addition, everything about them is different. The velocities are different, the angles are different, the amount of time she spends going in each direction is different. So trying to add them together doesn't give us any useful information. So if the problem is asking for final displacement, I have to begin working this problem by analyzing each leg independently. So in order to do that, the first thing I have to notice is that I'm traveling in a velocity of meters per second, but I'm traveling for a period of hours. So I'm going to have to convert that so that I've got the same unit so that my equations will work with one another. So I'm going to refer to this as leg A and leg B as I start working this problem. So in leg A, what I find is that she's traveling for 2.3 hours, and I need to convert that to seconds. So if I have 2.3 hours, in 1 hour there are 60 minutes, and in 1 minute there are 60 seconds, so 60 times 60 is 3,600, so 1 hour has 3,600 seconds in it. And so hours will cancel out, and if I take 2.3 times 3,600, I get 8,300 seconds, and that's the two significant figures. Now that I have my time in seconds, I can use delta x equals v sub 0 t plus 1/2 at squared to figure out what her displacement is on this leg of the journey. There is no acceleration because my velocity is constant, so this piece of it's going to drop out. So delta x then equals my initial velocity, which is 0.92 meters per second times 8,300 seconds, which gives me, let's see, 7,600 meters. is the displacement for the first leg of the journey. Now I will need to do exactly the same thing for the second leg of the journey. Again, they're taken at 2 separate times. They're not related to each other. So if I have 1.2 hours, I first need to convert that to seconds. So I'll do the same thing that I did over there, where my hours will cancel out. And that gives me 4,300 seconds for this piece. Then if I'm going to calculate the delta x, I'm going to take 0.56 meters per second times 4,300 seconds, and that's going to give me a displacement of 2,400 meters. All right, so I now have 2 displacements in 2 different directions. I have 7,600 meters, but this was at 113 degrees because that was the first leg of the journey. I have 2,400 meters, but that was at 220 degrees because that was the second leg of the journey, okay? Now that I have 2 displacements, since I'm being asked for the final displacement, again, this is adding 2 separate vectors together. So now I can go to what I learned in Module 3, and we can add these 2 vectors together. So I'm going to set this up just like I did back in Module 3. I'm going to kind of set up a chart where here's my x component and here's my y component. So the x component of the first leg is going to be 7,600 meters times the cosine of 113 degrees to give me just the x component. And that's going to give me, if I could have my glasses on so I'd actually see what I was doing, it would help. We're going to have a negative 3.0 times 10 to the third meters as the x component. The y component is going to be 7,600 meters times the sine of 113 degrees. And that is going to give me 7.0 times 10 to the third meters. Okay, so that's leg A. I'm going to do leg B the same way. I've got 2,400 meters. So I have 2,400 meters times the cosine of 220, which is going to give me a negative 1,800 meters. And you'll notice that all of these are going to have 2 significant figures because my displacement always had 2 significant figures because my initial velocities all had 2 significant figures. Okay, then the y component of that is going to be 2,400 meters times the sine of 220 degrees, and that's going to give me a negative 1,500 meters. And again, remember I had told you you need to be checking to make sure that these things are logical. This component A is in the second quadrant, and so I would expect a negative x and a positive y, and that's what I have. And then if component B was starting at the origin, it would be down in the third quadrant where I would expect both x and y to be negative, and that is what I have. So you want to constantly be thinking about those things as you're going through that to make sure you're not dropping negative signs by accident or making any mistakes like that. So when I add this together, this is going to be a negative 4,800 meters in the x direction, and this is going to be a positive 5,500 meters in the y direction. So now that I have the 2 components, I'm going to use the Pythagorean theorem to calculate the final magnitude. So that's going to be the square root of a negative 4,800 meters squared plus 5,500 meters squared. And when you crunch those numbers through, that gives you 7,300 meters. Okay, and again, as I said, this should be bigger than both of those, and it is. To find the angle, I have to take the inverse tangent of the y component, which is 5,500 meters, over the x component, which was a negative 4,800 meters. Now I would expect that the displacement vector is going to be coming this direction. These are actually velocity vectors, but even if I would have graphed the displacement vectors, they're still going to be similar to this. They're going to be at the same angle, and this one is going to be about 3 times as long as this one, which is approximately what I have drawn here. It's not exactly the same as your initial velocity vectors were, but I can still have enough of a picture in my head to know that it's still going to be coming up in this second quadrant. So if that angle doesn't come up that way, I know I've made a mistake someplace. When I do that, I get a negative 49 degrees, which again is what I would expect from a negative x component and a positive y component. So this is a negative 49 degrees. If it's up in that second quadrant, that means I have to add 180 degrees to it, and that's going to give me 131 degrees. So I'm going to have 7,300 meters at 131 degrees. So there is my final answer. Now, that may look very, very long. It is long. I'm not gonna mince any words. I'm not gonna try to pull the wool over your eyes and say, oh, that's not a bad problem to work. It's long. It just is long. But there's nothing in this problem that you don't already know how to do. You just have to put all the pieces together. You have to look at it and say, okay, first of all, I have 2 different segments of the journey that are not related to each other. Then I've got to make sure my units match, which is stuff we've done before. I'm going to analyze each specific piece of this journey so that I can calculate the displacement. Then when I have 2 displacement vectors and I want overall displacement, then I have to separate them into x and y components, figure out what the individual components are, and then use the same methods that we used back in Module 3 to figure out what the resultant vector is. So again, there's nothing new here. It's just that we're putting all of the pieces together now. So yes, the problems are long, but I've tried to allow you plenty of time to work with them. So be patient with yourself and just remember to try to break each of the problems down into the segments that you already know how to do.